Okay, so now we're on the fourth section of chapter 3. Real zeros of polynomials. Rational zeros of polynomials. Descartes' rule of signs for upper and lower bounds. And using algebra and graphing devices to solve polynomial equations. Now, as I keep saying in this chapter, there's a lot of information here, and that information helps you to make decisions that save you time. So when you are solving these equations or attempting to find the zeros, you will have this knowledge in your head that will help you make the decisions on which ones would be better than others to choose. So let's take a look. Now the factor theorem tells us that finding the zeros of a polynomial is the same thing as factoring it into linear factors. So in this section, we're going to study some algebraic methods to help us find the real zeros of a polynomial and therefore factor the polynomial. We'll begin with rational zeros of a polynomial. Okay, so let's consider the following polynomial. We have x minus 2, x minus 3, and x plus 4. Just by inspection looking at this, I can see that if I have 2 in here, I will get 0. If I have 3 in here, I will get 0. And if I have negative 4 in here, then I will get a 0. So the zeros again are 2, 3, and negative 4. So when the polynomial is expanded, we get a constant of 24. So that means that we can multiply the opposites of these, which would be in our factor, negative 2, negative 3, and positive 4 to get that value of 24. So what that means is the zeros of the polynomial are all factors of the constant term. Now, taking a look at that, we're going to take a look at the possibilities of all rational possibilities that could be zeros of a polynomial. And how to do that is I'm going to take P, which is the factor of the constant coefficient, A0, over here. So remember before we said if it's factors of our constant, and Q is the factor of the leading coefficient of A sub n. If I do this and I put all the possible factors of P over all the possible factors of Q, I can narrow down what my zeros are. Now you might think, well, that could be a lot. Well, it could be, but it's a lot less than infinity by just taking a shot in the dark and just guessing. So let's find the rational zeros of x cubed minus 3x plus 2. The leading coefficient is 1, and we have positive 2 here, so I'm going to take a look at the constant term 2. And this is really a simple one because we have prime numbers for both the leading coefficient and the constant term. So I only have possibilities of plus or minus 1 and plus or minus 2. And it'll always be plus or minus those values. So if I try each one of these into, and actually they have you here plugging them into here. Not sure why they're doing this instead of synthetic division, but we'll see. plug it in. We want to see if we get 0. There we go. On that one, I did get 0. On -1, I get 4, so that's not a 0. On 2, I will get 4, so not a 0 again. And on -2, I get another 0. So using this method shows me what 2 of the factors are. Well, if I have 2 factors of the 3, I can find the third one. So we're going to list the possible rational zeros using rational zeros theorem. Then we're going to divide using synthetic division, which is easier than what they just did to evaluate. And then we're going to repeat steps 1 and 2 for the quotient. And we're going to stop when we get to something that factors easily, which will either be a quadratic or a linear. And I will show you that. So here I have a cubic again, and if I'm looking at synthetic division, I'm going to have coefficients of 2, 1, -13, and 6. And I did, upon inspection, check my exponents to make sure they went 3, 2, 1, 0, and none of those were missing. Now I have to take all the possible factors of the constant term, which is 6. So possible factors of 6 would be plus or minus 1, plus or minus 6, because 1 times 6 is 6, -1 times -6 is 6. Then I have plus or minus 2, and also plus or minus 3. Once I get those numbers, I'm going to take those and place them over each one of the other numbers. So I have 1 over 1, 2 over 1, 3 over 1, 6 over 1, and then 1 over 2, 2 over 2, 3 over 2, 6 over 2. So again, to make that a little clearer, these were all my factors of 6. And I put those, each one of those, over all the factors of 2. Now, you'll see here that there's plus or minus in front of each one, so that means each one of these represents 2 different numbers. Some of these numbers may actually reduce to be the same number. If you take a close look here, you can see that I have 1 over 1, and then I have 2 over 2. Well, that's still 1. So we can eliminate one of those and just put plus or minus 1 here. So I'll have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and then the fractions, which are 1/2 and 3/2. Now I want to test each one of these to see if there is 0. So let's test 1. It's not a 0 because I get -4 as a remainder. But when I test 2, again, bring down the first term, multiply, add straight down, multiply again, add straight down, multiply again, add straight down. I get a 0. So what does that tell me? That tells me that x minus 2 is a factor. It also tells me that this is what's left. So I started with a cubic and now I have a quadratic. So I have this as a factor, and then I have 2x squared plus 5x minus 3. Now, why did I do that? Well, because it's a quadratic. And since it's a quadratic, I know I can either factor that to solve it, or I can use a quadratic formula, or I can use your favorite, which is completing the square. So first, I probably want to see if this will just factor. And the reason is that I won't have to check the rest of my numbers. So there it is, x minus 2 times 2x squared plus 5x minus 3. And I can, in fact, factor that to be this. So this factored to this. How do I know that? I factored it using my methods for factoring. Either you do guess and check, or you do the way that I showed you with factor by grouping. So now I can find all my solutions. I see if I place 2 in here, that it'll be a 0. I see that if I place 1/2 in here, I will get a 0. And I see if I place -3 in here, then I'll get a 0. Descartes' rule of signs and upper and lower bounds for roots. All right, so to describe this rule, we need the concept of variation of signs. We have a polynomial with real coefficients written in descending order. So I have my 7th, missing an x to the 6th. Excuse me. So I need to keep that in mind if I'm going to do synthetic division with this later. X to the 4th, x squared, x to the 1st, and x to the 0. I don't need to put the 0x to the 4th in right now because 0 is neither negative nor positive, so I don't need it for my variations of signs. Variations of signs is simply that. Where do the signs change from positive to negative? Well, right here is positive, and then this is negative, so that changes signs. Now this is negative to negative, so it does not change signs. That's why there is no arrow here. But from here to here, this changes signs, so there's another variation. Then I have positive to positive, which does not change signs, and now I have positive to negative, and there's 3 variations of signs. Now, it's not always going to be alternating like that, so don't try to remember that part of it. Now again, this gives you information to know, and to know something means you have to study it. So if you need to know something, you have to study it. Okay, so the number of positive zeros, which means answers when we get 0 as a remainder, the number of positive real zeros is either equal to the number of variations in sign or less than by an even whole number. What does that mean? Well, in the last problem, I had 3 variations of signs. So that means I either have 3 or less than by an even whole number. So I either have 3 or, if I go down by an even number, 3 or 1. Now, the second part of that says the number of negative real zeros is equal to the number of variations in signs if I put a negative x in there, or less than by an even whole number. So the first one is just examining it on its own. I don't make any changes, and that tells me how many positive real zeros I have. But if I want to know how many negative real zeros I have, I'm going to put in negative x. Now you might be thinking, why do I want to do this? Well, let's say you have about 20 different numbers to check to see if they're solutions, which is not even a big amount when you're using what we're looking at here. If I get 3 positive numbers to work, I can eliminate all my other positive numbers that I have in my list, and that saves me time. So here I'm going to take a look at the number of positive and negative reals. I'm going to take a look at any kind of changing of signs. This is positive to positive, does not change. Positive to positive, does not change. Positive to negative, there's one change, and then negative to negative doesn't change. So that's really helpful because it tells me that I only have one positive number as an answer to this x to the 6th polynomial. So if I find the positive number, then I can cross out all the other positives and move on. Now if I put negative x in, let's see what happens. Anywhere where there's an odd exponent, it will change the sign. So now I have positive to negative once right here. I have positive to negative again here, and positive to negative here. So that means I will have 3 or 1 negative answers to my problem. Now you might think, well, if I could only have 1 or 3, then that only adds up to 4, and I have an x to the 6th, so how can that be? Because I thought I really had 6 answers. Well, this tells me that either the other ones are not rational answers, or maybe I have multiplicities of some of those numbers that work more than once. Okay, so now we say that A is a lower bound and B is an upper bound for the zeros of a polynomial for every real C of the polynomial that satisfies C is going to be bigger than or equal to A and less than or equal to B. So the next theorem helps us find the bounds. And again, we might be thinking, why are we examining the bounds? Well, if we divide P of x by x minus B, and B is bigger than 0, so it's P minus B. Using synthetic division, if the row contains the quotient and the remainder, so if the quotient and the remainder has no negative, then B will be the upper bound. So why do I care? Well, I care because I have all these numbers again that I'm checking. And let's say I use the number 3. And after I use the number 3, I look below and I see every single one of my entries and my quotient and my remainder are positive at the end. Well, that tells me there is no number bigger than 3 that works. So once again, I can eliminate anything that's bigger than 3. Again, if I have P of x, excuse me, and A is less than 0, and I'm using synthetic division, if the row that contains the quotient and the remainder alternate, then that is the smallest number that I have. So I can find which one is my largest number, and I can find which one is my smallest number. And once again, that will help me eliminate some of the other possibilities and save me time. And that's the whole point of all of these, is to save you time. So let's show all the real zeros of the polynomial. Here, I'm going to take a look. I know that all my possibilities are between -3 and 2, so I'm going to check. First, I'm going to try 2. And when I check 2, I see that all of these answers are positive. Since they're all positive, that tells me that in fact 2 is the biggest number that I have to be a 0 in this problem. Now I can check -3 to see if it is in fact the lowest bound because they told us it was. See how the signs alternate from positive to negative, negative to positive, positive to negative, and negative to positive. That tells me that there is no number smaller than 3 that will be a 0 for this polynomial. So if I have other numbers listed in my possible rational roots, we can eliminate them as not possible anymore because we have this theorem. Since neither -3 nor 2 is a 0, the remainders are not 0 in the division table, and all the real zeros have to be in between these two numbers. All right, we're going to take a quick look at using some algebra and graphing devices to solve polynomial equations. Here we're going to find the real solutions of the following equation rounded to the nearest tenth. So to solve the equation graphically, we will graph this. And we're going to use the upper and lower bounds theorems to find the two numbers in which the solutions must lie. So this allows us to choose a viewing window rectangle that is certain to contain all the x-intercepts because the x-intercepts are my solution. So we'll use synthetic division to proceed by trial and error. We try the whole numbers 1, 2, 3 as potential candidates. And we see that when we get to 2, we have all positive. And we see when we get to -3, we have alternating signs. That will tell us that all of our answers have to be in between -3 and 2. So if I use a viewing rectangle of -3 and 2, that'll help me to take a close look at my polynomial. And here it is. So now I can see my answers are going to be here and here. And I can trace that to try to find the solutions. So if I zoom in and trace to the nearest tenth, I can see that my zeros for this particular polynomial is -2, 3, and 1, 3. And that will be all for this section. So the next one will come next week.